Okay, this is lesson 7 in your workbook on page 130, and we're going to explore a little bit about relationships within our tables and how a proportional relationship might look different from one that's not proportional. So this first lesson is just a little warm-up, adjusting a recipe. A lemonade recipe calls for the juice of 5 lemons, 2 cups of water, and 2 tablespoons of honey. We're going to make new versions of this recipe, and number 1 is one that would make more lemonade, but tastes the same. Well, if we're going to make more lemonade, we're going to need more water, right? So we want it to taste the same, so we're going to have to adjust each amount by the same amount. So let's double the recipe. 5 lemons would become 10 lemons. 2 cups of water becomes 4 cups of water. And 2 tablespoons of honey becomes 4 tablespoons of honey. All right, you have to change each ingredient by the same amount. Now, if we wanted to make less lemonade, we need less water. So, and we want it to taste the same. So we got to adjust each amount the same. So let's take it times a half. So we're going to use 2½ lemons, which would be half of 5, 1 cup of water. Now we have less lemonade and 1 tablespoon of honey. Okay, both of these recipes will taste identical to the first one. We just have more of the first and less of the second. So number 3, now I want to alter this. I want it to have a stronger lemon taste. So if I want more lemony taste, I need more lemons, right? So let's do 7 lemons. But we're going to make the same amount, 2 cups of water and 2 tablespoons of honey. That just gives the same recipe a little more lemony taste. And if we want a little more weaker lemony taste, we're going to do less lemons. So instead of 5, let's do 3 lemons. 2 cups of water and 2 tablespoons of honey. Okay, so we can adjust our ratios in our recipe to give us more of a certain flavor or less of a certain flavor, or to just make more and have the same thing. Okay, the next activity is visiting the state park. Entrance to a state park costs $6 per vehicle, plus $2 per person in the vehicle. How much would it cost for a car with 2 people to enter the park? Or 4 or 10? So we want to fill out this chart. So if we have 2 people, right, each of those people are going to pay $2, and we're going to pay $6 for the car to get into the park. So that would be $10. 4 plus 6. Now if we had 4 people, we're going to take 4 times 2, because it's $2 for each of them, 6 for the car. 8 plus 6 gives us $14. And I'm going to let you figure out what 10 people in a car would cost. What would be the cost for 10 people in the car? Then it says for each row in the table, if each person in the vehicle splits the entrance cost equally, how much will each person pay? So for this first row, it was $10. And there's 2 people in the car, so they're each going to pay $5, right? We're splitting it 2 ways. And if their cost was $14, but we had 4 people in the car, we're going to divide by 4. And you get $3.50 for each person. And then you're going to have to do, what if there were 10 people in the car, whatever you got in the table, fill that in and see what the cost would be for each person. So how would we determine cost for a bus with 50 people? Well, we're going to do it the same way we did up here. We have 50 people. They're each going to pay $2. And then we have $6 for the entrance fee. That's going to give us $106. Okay, is the relationship between the number of people and the cost a proportional relationship? So you're looking for that constant of proportionality. Remember, you have your x in your table and your y over x. Well, that's what we did in this problem right here. Y over x, 10 over 2. 14 over 4. Something over 10. And are these numbers the same? No, they're all different. So it is not a proportional relationship. And how do we know it's not proportional? Because the cost per person is not the same. For each row. Right, and the cost per person is our COP, the constant of proportionality. Okay, let's go on to running laps, 7-3. Hans and Claire were running laps around the track. The coach recorded their times at the end of laps 2, 4, 6, and 8. So for Hans' run, we need to find how many minutes per lap. So in this case, you're doing 4. Again, this is your X, this is your Y, over 2, which gives us 2 minutes per lap. And then you have 9 over 4. Just use your calculator. 9 divided by 4 is 2.25 minutes per lap. 15 divided by 6. 23 divided by 8. Okay, for each one you need to calculate how many minutes per lap. Then for Claire's run, we're going to do the same thing, but now we have 5 over 2, which is 2.5 minutes per lap. In 10 minutes, she ran 4 laps. 10 divided by 4, oh, I can tell. That's the same thing as 5 over 2. That's 10.5 minutes per lap. 15 over 6. 15 divided by 6 is 2.5 minutes per lap. And if we do 20 divided by 8, we get the same thing, 2.5 minutes per lap. So who is running at a constant pace? Is it Claire or is it Hans? How do you know? Well, hopefully you can see that Claire, no matter how many minutes she ran for, her speed was the same, 2.5 minutes per lap. 2.5 minutes per lap. Hans ran 2 minutes per lap, and then he got a little bit slower. It took him 2 1/4 minutes to run the next part of the laps. And then when you did 15 divided by 6, you should have got 2.5 minutes per lap. So again, he's slowing down the more laps he runs. It's getting slower and slower. So who runs at a constant pace? Claire. And how did you know? Because her speed was the same throughout her run. Her speed was the same throughout her run. So we're going to write an equation for the relationship between distance and time for anyone that is running at a constant pace. So remember, when you write a equation, it should be in the form y equals kx, where k is your constant. So can we write an equation for Hans? No, because he didn't have a constant, right? His speed is changing throughout, so this is not a proportional relationship. 4 to 2, 9 to 4 are not equivalent ratios. But in Claire's case, 5 to 2, 10 to 4, 15 to 6, these are all equivalent ratios, so we can write an equation, a proportional equation, which would be y equals the constant. So in this case, y was our time, and Claire's constant was 2.5 minutes per lab. And we're going to multiply that times x, which was our distance. So we could shorten that by just saying t equals 2.5 times the distance. Okay, so the key to writing these equations, they're always going to be in the same form, y equals kx, is identifying your x and your y in your table so that you can just look to see what it is. In this case, y was time, x was distance. Okay, for your notes today, page 11 in your notes packet, we're going to write lesson 7. Okay, the learning target is I can decide if a relationship is represented by a table, could be proportional, and when it's definitely not proportional. So we just did that with Claire and Hans. Here's an example of a smoothie. This is the size. This is your cost. So this would be your x. This is your y. So my cost per ounce is my constant of proportionality, right? 0.75, 6 divided by 8. 9 divided by 12 was also 0.75. 12 divided by 16. Is this a proportional relationship between cost and size? Yes, it is, because there's equivalent ratios, okay? So there, I want you to write this down. There's a proportional relationship between the cost and size of a smoothie because the cost per ounce is the same for every size. And they have equivalent ratios. The ratios of cost to size are the same. Now, if the relationship can be represented by an equation of the form y equals kx, then we can be sure it's proportional. So in this case, my y was my cost. My cost is equal to the constant, 0.75, times x, which was the size, s. C equals 0.75 s would be my equation. Okay, you have an assignment for lesson 7 in Schoology. You need to go to your workbook and do the practice there first before you enter that. Have a great day, Falcons.